Next, given that ABCD is a parallelogram again, prove that each pair of opposite sides are congruent. For assistance, I've drawn in the diagonals since this is the way that we're going to do this. We're going to use our theorems from triangles in order to help us. Note that the diagonals create two pairs of triangles, and we want to show that the two triangles are going to be congruent. Now, we can pick our triangles in a multitude of different ways. Our goal is to show, and this is always the first step you want to take with a proof, our goal is that we want to show that the opposite sides are congruent. That is, we want to show that AD is congruent to BC. And we want to show that AB is congruent to DC. And so since we have two pairs of sides that we want to show are congruent, we're going to need to use some of our triangle theorems to help us. In order to do this, let's draw the two triangles that we're considering using. The triangles that I think are best to use are the following. We'll use the two upper halves. We'll use triangle A, D, or B. And the other triangle that we're going to use, which I will draw in another color, is going to be triangle D, C, B. And so if I can show that triangle DAB is congruent to triangle BCD, I can use, not triangle, I can use CPCTC, that congruent parts of congruent triangles are congruent, to get my answer. So we know that that is where we're heading. Remember that CPCTC requires me to first of all have two pairs of congruent triangles. And so before I can use it, I need to show that the triangles are congruent first. Since we are trying to show that two sides of each triangle are congruent to the others, we are not going to be able to use SSS or SAS. So to get the triangles congruent, the only tool I'm going to be able to use is ASA, which means I need to find two angles and a side that is congruent to each other in both pairs of triangles. The side is fairly simple, and we'll mark it in green. We have that DB is congruent to itself. Both triangles share DB. Let's mark DB in green. Maybe you can't see it. Maybe we should do yellow instead. There's DB. We want to show that DB, well, we don't have to show it, we know it, is congruent to itself, or BD. And this is self-congruence. Everything is congruent to itself. Remember that we call this the reflexive property. Everything is equal to itself. So we have a side, and we need the two angles that bound the side, which means I need to get that angle, let's call this angle ADE, is congruent to, we can use the opposite angle, angle CBE. And the reason that these two angles are congruent to each other is because of the fact that they're alternating interior angles. So we have that the measure of angle ADE is going to equal the measure of angle CBE because they are alternate interior angles. Right now, I'm just writing down all of the things that I can see. I'm not worrying about whether or not they're consistent and well ordered. That's what the two-column proof will do for us in a moment. Likewise, we can find that another pair of angles, let's put them in a different color. Let's use this color here. We'll find that angle ABE is going to be congruent to angle CDE. And this is on the principle as well that they are alternate interior angles. So the measure of angle ABE is going to equal the measure of angle CDE because they are also alt-int angles. And now I have what I was looking for. I have a side and I have the included side and two angles that bound the side. And so I can use the ASA theorem to show that the two triangles that I've highlighted are congruent. So here we go. We have our statement and we have our reason. First of all, we know that ABCD is a parallelogram. And that's given. The other thing that we need in order for this to work is we need to remember that AD is parallel to BC. And this is by the definition of a parallelogram. Furthermore, the diagonal DB is a transversal. And this is by definition of a transversal. Transversal, remember, is simply a line that cuts two other lines. Now, since the two lines that it cuts are parallel, we have a few theorems that we can use. We can use the fact that angle ADE, the measure of angle ADE, is equal to the measure of angle CBE, and we said that that was on account that they're alternate interior angles. And the alt-int angle theorem says that if the two lines are parallel, the alternate interior angles are congruent. Furthermore, we found that the measure of angle CDE is equal to the measure of angle ABE, and this was on account that they were alt-int angles as well. The same theorem that said that the alternate interior angles of parallel lines are going to be equal in measure. Consequently, we now have the last part of this, which is that DB is going to be congruent to itself. And that is on account of the reflexive property. So now I have the two angles and the included side. So I can conclude by the ASA theorem that triangles DAB and triangle BCD are congruent to each other by the ASA theorem. And because those two triangles are congruent to each other, we now can say that side DC is congruent to side AB, and that side AD is congruent to side BC, and both of these are an account of CPCTC. Congruent parts of congruent triangles sorry, not congruent parts, corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. Let's step back a little bit and make sure that we understood what has happened here. I needed to prove that the two opposite sides were congruent to one another. In order to do that, I split the parallelogram through one of its diagonals. You could have done it using this diagonal here, AC, as well, and gotten the same result. In order to do this, I noticed that I did not know any information about the sides, and so side, side, side for the two triangles was not going to work, which meant that, and nor could side, angle, side, since I would need to know something about two sides of each triangle. I only know something about one, the diagonal, which is that it's congruent to itself. And so the only other theorem that I could use was the ASA theorem. So setting out to use the ASA theorem, I had one side and I needed to find the two angles that were congruent to the other two. I was able to use properties of alternate interior angles to help me with that. But since I was going to use alternate interior angles, there were some things that I had to establish first. I needed to establish that the lines that I were finding the alternate interior angles to were parallel, and I needed to establish that those parallel lines were cut by a transversal. Once I have parallel lines cut by a transversal, then I can use the alternate angle theorem. Once I was able to do that, I was able to conclude that the two pairs of angles were congruent to one another.